What if I told you there's a welding process so versatile that it can join thin sheet metal for automotive bodywork and thick steel plates for structural fabrication? A process that's beginner-friendly yet powerful enough for industrial production? Welcome to the world of gas metal arc welding, also known as MIG welding or GMAW. This is the welding process that changed manufacturing forever, and today, I'm going to show you everything you need to know about it. By the end of this video, you'll understand how GMAW works, the equipment you need, the techniques professionals use, and the common mistakes to avoid. So grab your welding helmet, and let's get started. Don't forget to subscribe and hit the notification bell, we've got tons of welding content coming your way. So, what exactly is gas metal arc welding? Let's break it down. GMAW, commonly called MIG welding, which stands for metal inert gas, is a semi-automatic or automatic arc welding process. Here's how it works in simple terms. A continuous solid wire electrode is fed through a welding gun. When you pull the trigger, the wire feeds forward and an electrical arc is created between the wire and your workpiece. This arc generates intense heat, we're talking around 6,500 degrees Fahrenheit, which melts both the wire and the base metal. But here's the critical part. While all this is happening, a shielding gas flows through the gun, surrounding the weld pool. This gas shield protects the molten metal from atmospheric contamination, specifically oxygen, nitrogen, and hydrogen, which would otherwise weaken the weld. The beauty of GMAW is that as the wire melts, it's continuously fed, so you get a smooth, consistent weld without having to stop and change electrodes like you would with stick welding. GMAW was developed in the 1940s for welding aluminum and other non-ferrous metals, but it quickly became popular for steel welding due to its speed, versatility, and ease of use. Now let's talk about the equipment you need for GMAW. Understanding each component is crucial for getting quality welds. The welding power source. First up is your power source or welding machine. GMAW uses constant voltage DC power. This is different from stick welding, which uses constant current. The power source can range from small 120-volt machines perfect for hobbyists, all the way up to industrial 480-volt units. Most modern machines are inverter-based, making them lighter and more efficient than the old transformer models. The wire feed system. Next is the wire feeder. This mechanism pushes the electrode wire from the spool through the liner and out the contact tip. The feed speed is adjustable and works in harmony with your voltage setting. Too fast, and you'll get a stubbing, spitting arc. Too slow, and the wire burns back. The welding gun. The MIG gun is your control center. It houses the contact tip where electrical current transfers to the wire, the nozzle that directs the shielding gas, and the trigger that controls everything. Guns come in different amperage ratings: 150 amps, 250 amps, 350 amps, and higher. They can be air-cooled for lighter work or water-cooled for heavy industrial applications. Shielding gas system. You'll need a gas cylinder with a regulator and flow meter. The regulator reduces the high cylinder pressure to a usable level, while the flow meter lets you control the gas flow rate, typically between 15 to 25 cubic feet for most applications. Consumables. Don't forget consumables. You'll need wire spools in the correct diameter and material, contact tips that match your wire size, nozzles or cups, drive rolls sized for your wire, safety equipment, and absolutely essential, your safety gear, auto darkening welding helmet rated for MIG welding, welding jacket or leather sleeves, welding gloves, safety glasses, proper ventilation or respirator when needed. Types of shielding gases. The choice of shielding gas dramatically affects your weld quality, penetration, and appearance. Let's explore your options. 100% argon. Pure argon is the go-to gas for welding aluminum and other non-ferrous metals. It provides excellent arc stability and produces minimal spatter. The arc tends to be narrower with argon, giving you good control. However, for steel, pure argon gives inadequate penetration and an unstable arc. 100% CO2, carbon dioxide. Carbon dioxide is the most economical choice for welding carbon steel. It provides deep penetration, which is great for thicker materials. The downside? CO2 produces more spatter, a harsher arc, and can lead to oxidation in the weld. You'll notice a less aesthetic bead profile compared to mixed gases. Argon, CO2 mixtures. This is where most steel welding happens. The most common blend is 75% argon and 25% CO2, often called C25 or 75-25 mix. This combination gives you reduced spatter compared to pure CO2, better arc stability, smoother weld appearance, good penetration, versatility across different materials and thicknesses. For even cleaner welds, some fabricators use 90-10 and 95-5 argon, CO2 mixers, especially for thin materials or when appearance is critical. Argon, zero oxygen mixtures, adding a small amount of oxygen, typically 1 to 2% to argon, is used for stainless steel and some carbon steel applications. The oxygen improves arc stability and weld pool fluidity. Try mix gases. Some specialized applications use 3 gas mixtures combining argon, CO2, and helium. These are typically used for stainless steel or when you need specific penetration characteristics. Practical tips for beginners: I recommend starting with 75-25 argon, CO2 for steel. It's forgiving, readily available, and works well across a wide range of applications. As you gain experience, you can experiment with different mixtures to optimize for your specific needs. Wire electrodes or materials. Just like shielding gases, choosing the right wire electrode is crucial for successful GMAW. Let's talk about what's available and when to use each type. Solid wire versus flux cord wire. First, understand that GMAW typically uses solid wire, but there's also flux cord wire, which we'll touch on briefly. Solid wire relies entirely on external shielding gas, while flux cord has a flux compound inside that can provide shielding. Wire diameters. Common wire sizes include 0.6 mm for thin materials, sheet metal. 0.8 mm, the most versatile size for general use. 0.9 mm popular for 3 mm to 6 mm. 1.0 mm for thicker materials and higher amperage. 1.6 mm and larger industrial heavy-duty applications widely used. Steel wire, ER70S6. This is your workhorse for carbon steel. The ER means it can be used for both electrode and filler rod. The 70 indicates 70,000 psi tensile strength. The S means solid wire, and the 6 refers to the deoxidizer content. ER70S6 has higher silicon and manganese, making it great for welding on dirty or rusty steel, perfect for real-world conditions. Steel wire, ER70S3. This wire has lower deoxidizers, making it better for clean, bare steel. It produces less silicon islands on the weld surface but requires cleaner base material. Stainless steel wire. For stainless, you'll use wires like ER308L for 304 stainless, ER316L for 316 stainless, and so on. The L designation means low carbon content, which prevents carbide precipitation and corrosion. Aluminum wire. Aluminum wire is softer and requires special drive rolls with U-shaped grooves instead of V-shaped. Common types include ER4043 for general purpose and casting repair, and ER5356 for structural applications and higher strength. Wire storage. Here's a pro tip: store your wire properly. Moisture can cause porosity in your welds. Keep wire spools in sealed bags with desiccant packets when not in use. Aluminum wire is especially susceptible to oxidation. Matching wire to base metal. Always match your wire to your base metal chemistry and thickness. Using the wrong wire can result in weak welds, cracking, or corrosion issues down the line. One of the most important concepts in GMAW is understanding metal transfer modes. This is how the molten metal transfers from the wire to the weld pool. There are 4 main types, and each has specific applications. Short circuit transfer. This occurs at lower voltage and amperage settings. The wire actually touches the weld pool, creating a short circuit that pinches off a droplet of metal. This happens between 50 to 200 times. Characteristics: lower heat input, perfect for thin materials. Minimal spatter when set correctly. Good for out-of-position welding. Vertical, overhead, creates a distinct buzzing or crackling sound. Not suitable for thick materials, lacks penetration. Typical settings: 50 to 200 amps, 15 to 20 volts. Globular transfer. This is generally an undesirable transfer mode that occurs in the transition between short circuit and spray transfer. Large, irregular droplets form at the end of the wire and drop erratically into the weld pool. Characteristics: heavy spatter, poor weld appearance, inconsistent penetration, usually avoided by adjusting parameters. Spray transfer. At higher voltage and amperage, with argon-rich shielding gas, the wire transfers in a continuous stream of tiny droplets. Think of it like a spray paint effect. Characteristics: hundreds of droplets. Smooth, quiet arc, deep penetration, excellent for thick materials. Requires argon-rich gas, 85% argon minimum, limited to flat and horizontal positions due to large weld pool. Higher heat input. Typical settings: 200 plus amps, 22 to 28 volts for steel. Pulsed spray transfer. This is an advanced technique where the machine pulses between a low background current and a high peak current. During the peak, one droplet transfers per pulse. Characteristics: combines benefits of spray quality with short circuit, lower heat, allows spray transfer on thinner materials. Excellent for aluminum and stainless steel. Can be used in all positions. Requires sophisticated power source with pulse capability. Minimal spatter, excellent appearance. Now let's get into the actual technique, how you hold and move that MIG gun makes all the difference between a beautiful weld and a mess. Gun angles. Work angle. The work angle is the side-to-side angle of your gun. For most butt joints and flat welding, you want to hold the gun at 90 degrees to the workpiece perpendicular to the joint. For fillet welds, T-joints or lap joints, aim for a 45-degree angle, splitting the difference between the two surfaces. This ensures equal penetration on both pieces. Gun angles. Travel angle. The travel angle is the forward or backward tilt along your direction of travel. You have two techniques: push technique, forehand, gun pointed 5 to 15 degrees in the direction of travel. This produces flatter, wider beads. Less penetration, better for thin materials, cleaner looking welds. The saying is, if it looks good, you pushed it. Pull technique, backhand, gun pointed 5 to 15 degrees backward, dragging the puddle. This produces deeper penetration, narrower, more built-up beads. Better for thick materials, more spatter. The saying is, if it's strong, you pulled it. For most applications on mild steel, a slight push angle is recommended. Contact tip to work distance, CTWD, keep your contact tip about 1/4 to 3 by 8 inch from the workpiece. Too close and you risk stubbing, too far and you lose arc stability and gas coverage. Consistency is key. Travel speed, move at a steady pace, not too fast, not too slow. Too fast and you'll get a skinny, weak bead with poor penetration. Too slow and you'll create an overly thick bead that can trap slag and create poor fusion. A good rule of thumb: the weld bead should be about 2 to 3 times the width of your wire diameter. Weaving vs stringer beads. For most MIG welding, stringer beads, straight runs with no side-to-side motion, are preferred. They're faster, provide better penetration, and reduce the heat-affected zone. Weaving can be used for wider joints or specific applications, but keep the weave narrow, no more than 3 times the wire diameter. The weld pool. Watch your puddle. It should look like a bright, fluid circle or oval moving steadily along. You should see a slight ripple or shelf at the back of the pool. If the pool gets too large, speed up or reduce voltage. If it's too small, slow down or increase voltage. Practice drill. Start by running beads on flat plate. Focus on consistent travel speed, steady hand position, proper gun angle, watching the puddle, not the arc. Starting and stopping cleanly. Do this for hours before moving to joints. Build muscle memory. Getting your machine settings right is absolutely critical. Let's break down how to dial in the perfect parameters for any job. The relationship, voltage and wire feed speed. In GMAW, these two settings work together. Think of it this way: wire feed speed determines amperage, how much metal you are depositing; voltage determines arc length and arc characteristics. Most modern machines have preset synergic programs, but understanding the relationship helps you fine-tune. Starting point. Manufacturer's charts. Every machine comes with a parameter chart. These give you baseline settings based on material type and thickness. Wire diameter, shielding gas type. Always start here, then adjust based on what you see and hear. The sound test. A properly set GMAW arc should sound like short circuit, a steady sizzle or frying bacon sound. Spray transfer, a smooth hum or hiss. If you hear stuttering or popping, wire feed too slow or voltage too low. Loud crackling with heavy spatter, voltage too high or wire feed too fast. Machine gunning sound, good. You are in the ballpark for short circuit. Reading the arc, watch what the arc is telling you. Too cold, insufficient voltage, amperage, arc keeps stubbing out. Poor penetration, irregular bead with cold lapse. Lots of spatter sticking to base metal. Too hot, excessive voltage, amperage, burn through on thin materials. Excessive reinforcement, built up weld, wide heat affected zone. Potential for undercut at bead edges. Just right, smooth, fluid puddle. Consistent bead width. Minimal spatter. Good penetration without burn through. Nice rippled appearance, fish scales, FINETUNING process. Set wire feed speed for your material thickness. Adjust voltage until arc sounds and looks right. Make test welds. Adjust voltage first, affects arc stability, then adjust wire feed if needed, affects deposition rate, small changes. Move voltage by 0.5 volts increments. Gas flow rate, don't forget this. Set your flow meter to 15 to 20 CFH for indoor work with no wind, 20 to 25 CFH for outdoor or drafty conditions. Too low, porosity and contamination. Too high, turbulent gas flow pulls in air, wasting gas. Pro tip: the test piece. Always run a test bead on scrap of the same material and thickness before welding your actual project. Make adjustments on the test piece, not your final work. Let's talk about the different joints you'll encounter and how to prepare them for optimal welds. Butt joint, this is where two pieces of metal meet edge to edge on the same plane. Preparation, thin materials, under 3 mm, square edge, no gap needed. Medium, 3 to 6 mm, 1 to 2 mm root gap, slight bevel can help. Thick, over 6 mm, bevel edges to 30 to 35 degrees, leave 6 mm root face. Welding technique, single pass for thin, multiple passes for thick material. T-joint, fillet weld, one piece perpendicular to another, forming a T shape. Preparation, ensure pieces are square, 90 degrees, clean both surfaces thoroughly, no gap for most applications. Welding technique, split the angle at 45 degrees. Work angle bisects the joint. Can weld one side or both sides depending on strength requirements. Fillet weld size is specified by leg length. A 6 mm fillet has 6 mm legs on each side. Lap joint, two pieces overlap each other. Preparation, overlap should be at least 3 times the material thickness. Clean both surfaces. Trapped contaminants cause porosity. Clamp securely to prevent movement. Welding technique, angle gun to a thinner piece to avoid burn through. Fillet welds on one or both sides. Corner joint, two pieces meet at approximately 90 degrees at their edges. Types, open corner, no backing, closed corner, edges touching. Preparation, for thin materials. Edges can be square. For thick materials, bevel inside edge. Edge joint, edges of two pieces welded together, less common in structural work. Surface preparation critical steps, this cannot be overstated. Remove contaminants, grind off mill scale, rust, and coating. Remove oil, grease, and paint. Wire brush thoroughly. Wipe with solvent if needed. Clean metal guidelines. MIG can tolerate some surface contamination better than TIG. A 70S6 wire is more forgiving on dirty steel. But cleaner is always better. Fit up. Proper alignment is crucial. Use clamps, fixtures, or tack welds. Check for gaps. Excessive gaps need filler technique adjustments. Ensure pieces are flush and square. Tack welding. Small welds to hold assembly in place. Place tacks strategically to minimize distortion. Make tacks strong enough to hold but small enough to weld over. Space tacks to prevent heat buildup in one area. Joint access. Always consider how you'll access the joint. Can you get the gun in at the right angle? Is there room for your hand and proper gun manipulation? Design your assemblies with welding access in mind. Practice combinations. Master these in order. Flat butt joints on plate. Flat fillet welds, T-joints, horizontal fillet welds. Vertical up fillet welds. Overhead positions, if required. In the real world, you won't always be welding in a comfortable flat position. Let's cover the 4 basic welding positions and techniques for each. Flat position, 1G for groove, 1F for fillet. This is the easiest and most productive position. Gravity is your friend. Technique, work angle, 90 degree for butt joints, 45 degrees for fillets. Travel angle, 5 to 55 degrees push. Higher settings possible due to gravity helping control the puddle. Stringer beads, steady travel speed. Watch for undercut if moving too fast. Horizontal position, 2G for groove, 2F for fillet. The weld axis is horizontal, but the face is vertical. Challenges, gravity pulls the puddle downward. Risk of undercut on top edge, overlap on bottom. Technique for 2F, horizontal fillet, point gun slightly upward, 5 to 10 degrees, to fight gravity. Reduce voltage slightly from flat settings. Faster travel speed, aim for the upper plate more to ensure fusion. Technique for 2G, horizontal groove, may need to use slight weave to fill properly. Keep arc directed at leading edge to prevent sag. Vertical position, 3G for groove, 3F for fillet. Welding on a vertical surface, you can go up or down. Vertical up, recommended for structural welds, better penetration and strength. More control over puddle. Triangle or slight weave technique. Point gun slightly upward, 5 to 15 degree. Pause briefly at sides of weave. Reduce voltage 10 to 15% from flat settings. Reduce wire feed speed slightly. Let the puddle, shelf, form, then move up. Vertical down, for thin materials only, faster travel speed. Less penetration, not for structural work. Good for sheet metal, body panels. Point gun downward 5 to 10 degrees. Keep ahead of the puddle. Increase travel speed significantly. Overhead position, 4G for groove, 4F for fillet. The most challenging position, fighting gravity completely. Safety first, full coverage clothing, no exposed skin. Long sleeves buttoned at wrist. Leather jacket mandatory. Welding cap under helmet. Technique, reduce voltage 15 to 20% from flat settings. Reduce wire feed speed. Faster travel speed to prevent puddle from falling. Slight circular motion can help control puddle. Small weld beads, don't try to fill in one pass. Keep arc tight, CTWD consistent. Push angle slightly. Position transitions, when welding around a pipe or complex assembly, plan your start, stop points. Maintain consistent technique as position changes. May need to adjust slightly mid-weld. Practice position changes on scrap. Out of position tips, short circuit transfer is more manageable than spray. Smaller wire diameter gives better control. Watch the puddle constantly. Body position and comfort matter. Use stands, knee pads. Practice each position separately before combining. Certification positions. If pursuing welding certification, you'll be tested on 1G, 1F flat, 2G, 2F horizontal, 3G, 3F vertical, 4G, 4F overhead, 5G, 6G pipe welding positions. Master flat first, then progress to horizontal, vertical, and finally overhead. Don't skip ahead, each builds on the previous. Even experienced welders encounter defects. Let's identify common problems and, more importantly, how to fix them. Porosity, gas pockets, what it looks like, small holes or voids in the weld, can be surface or internal. Causes, insufficient shielding, gas coverage. Contaminated base metal, oil, rust, moisture, wind or drafts blowing gas away. Dirty wire or wet wire. Gas leak in system. Travel speed too fast. Solutions. Check gas flow rate, 15 to 25 cfh, clean base metal thoroughly. Shield work area from wind. Check all gas connections for leaks. Replace contaminated wire. Adjust nozzle to work distance. Spatter, what it looks like, small metal droplets scattered around the weld. Causes, voltage too high. Wire feed speed too high. Excessive wire stick out. Wrong shielding gas. Dirty base metal. Worn contact tip. Solutions. Reduce voltage in small increments. Adjust wire feed speed. Maintain proper CTWD. Use argon CO2 mix instead of pure CO2. Apply anti-spatter spray to nozzle. Replace consumables regularly. Undercut. What it looks like. A groove melted into base metal at the toe of the weld, not filled by weld metal. Causes. Travel speed too fast. Voltage too high. Arc too long, excessive stick out, improper gun angle. Solutions. Slow down travel speed, reduce voltage. Maintain proper CTWD, adjust gun angle, point more into the joint. Use slight weave to fill edges. Burn through. What it looks like, hole melted completely through the material. Causes: excessive amperage, voltage. Travel speed too slow. Too large wire diameter. Improper joint fit up with excessive gap. Inadequate backing or support. Solutions: reduce voltage and wire feed speed. Increase travel speed. Use smaller diameter wire. Improve fit up, close gaps. Use backing bar or copper backing. Skip welding technique for long gaps. Lack of fusion. What it looks like, weld metal doesn't bond to base metal or previous weld pass. Causes: insufficient heat, voltage too low, travel speed too fast. Improper gun angle, contaminated surface, excessive mill scale or coating. Solutions: increase voltage, slow down travel speed, adjust work angle to direct arc into joint root. Clean base metal thoroughly, remove all coatings and scale. Excessive reinforcement, overfill. What it looks like, weld bead excessively built up above base metal surface. Causes: travel speed too slow, excessive wire feed speed, too many passes. Solutions: increase travel speed, reduce wire feed speed. Proper weld sizing, don't overfill. Excessive reinforcement, overfill. What it looks like, weld bead excessively built up above base metal surface. Causes: travel speed too slow, excessive wire feed speed, too many passes. Solutions: increase travel speed, reduce wire feed speed. Proper weld sizing, don't overfill. Overlap, cold lap. What it looks like, weld metal rolls over base metal without fusing. Causes: insufficient heat, travel speed too slow, improper gun angle, puddle allowed to get ahead of arc. Solutions: increase voltage, adjust travel speed. Proper gun angle, push technique, watch and control the puddle. Inconsistent bead. What it looks like, irregular width, wavy pattern, uneven ripples. Causes: inconsistent travel speed, unsteady hand, varying arc length, poor body position. Solutions: practice. Focus on smooth, steady motion. Use proper body mechanics. Support your arms. Breathe and relax. Consistent gun angle and distance. The inspection process. After welding, visual inspection, look for surface defects. Check weld size and profile. Look for undercut, overlap, cracks. Check for uniform appearance. For critical work, destructive testing, X-ray, or ultrasonic testing. Remember, if it doesn't look good, it probably isn't good. Fix it now, not later. Now that you've mastered the basics, let's explore some advanced techniques that will take your GMAW skills to the next level. Pulse MIG welding. Modern inverter machines offer pulse capabilities. Alternates between peak current, droplet transfer, and background current, maintaining arc. 1 droplet per pulse, precise control. Reduces heat input while maintaining penetration. Excellent for thin materials, stainless, aluminum. Allows spray transfer at lower average currents. Can be used in all positions. Setup. Most machines have pre-programmed pulse settings. Adjustable pulse frequency affects bead appearance. Synergic control automatically adjusts parameters. Benefits: less distortion, better gap bridging, improved out-of-position capability, cleaner, more precise welds. Aluminum MIG welding. Aluminum presents unique challenges. Preparation: remove oxide layer immediately before welding. Wire brush stainless only. Oxide reforms quickly, weld soon after cleaning. Acetone to remove any oil or contamination. Equipment setup: use Teflon or nylon liner, softer wire needs it. U-groove drive rolls instead of V-groove spool gun for longer wire runs to prevent bird nesting. 100% argon shielding gas. ER 4043 or ER 5356 wire depending on application. Technique: push technique works best. Higher travel speeds than steel. Watch for burn through. Aluminum conducts heat rapidly. Preheat thick sections. Stainless steel GMAW, different considerations than mild steel. Shielding gas, trimix, 90% helium, 7.5 argon, 2.5% CO2, for excellent results. Or 98% argon, 2% CO2 minimum. Some use 90% argon, 10% CO2 but less ideal. Technique: maintain proper gas coverage. Stainless is unforgiving. Push technique: watch heat input. Stainless has lower thermal conductivity. Clean between passes with stainless brush, never use carbon steel brush. Back purging for critical applications.